Direct3D 11 programmable pipeline. Here you can see Direct3D 11 programmable pipeline. Here you can see Direct3D 11 programmable pipeline. The Direct3D 11 programmable pipeline is designed for generating graphics for real-time gaming applications. This diagram shows the data flow from input to output through each of the programming stages. The graphics pipeline for Microsoft Direct3D 11 supports the same stages as Direct3D 10 graphics pipeline, with additional stages to support advanced features. You can use the Direct3D 11 API to configure all of the stages that feature common shader cores. The rounded rectangular blocks are programmable by using HLSL programming language. As you will the input assembler stage, the Direct3D 10 and higher API separates functional areas of the pipeline into stages. The first stage in the pipeline is the input assembler IA stage. The vertex shader stage. The vertex shader VS stage processes vertices from the input assembler, performing per vertex operations such as transformations, skinning, morphing, and per vertex lighting. Vertex shaders always operate on a single input vertex and produce a single output vertex. This vertex shader stage must always be active for the pipeline to execute. If no vertex modification or transformation is required, a pass-through vertex shader must be created and set to the pipeline. Tessellation stage. The Direct3D 11 runtime supports 3 new stages that implement tessellation, which converts low detail subdivision surfaces into higher detail primitives on the GPU. Tessellation tiles or breaks up higher order surfaces into suitable structures for rendering. Geometry shader stage. The geometry shader GS stage runs application specified shader code with vertices as input and the ability to generate vertices on output. Stream output stage. The purpose of the stream output stage is to continuously output or stream vertex data from the geometry shader stage or vertex shader stage if the geometry shader stage is inactive to one or more buffers in memory. Rasterizer stage. The rasterization stage converts vector information composed of shapes or primitives into a raster image composed of pixels for the purpose of displaying real-time 3D graphics. The pixel shader stage. The pixel shader stage PS enables rich shading techniques such as per pixel lighting and post-processing. A pixel shader is a program that combines constant variables, texture data, interpolated per vertex values, and other data to produce per pixel outputs. The rasterizer stage invokes a pixel shader once for each pixel covered by a primitive. However, it is possible to specify a null shader to avoid running a shader. Output merger stage. The output merger OM stage generates the final rendered pixel color using a combination of pipeline stage. The pixel data generated by the pixel shaders, the contents of the render targets, and the contents of the depth stencil buffers. The OM stage is the final step for determining which pixels are visible with depth stencil testing and blending the final pixel colors. Here you can see input assembly stage is connected to vertex shader stage. Vertex shader stage is connected to hull shader stage. This hull shader stage is connected to tessellation stage or domain shader stage. Tessellation stage is connected to domain shader stage. Domain shader stage is connected to geometry shader stage, and geometry shader stage is connected to string output stage and rasterizer stage. Rasterizer stage is connected to pixel shader stage. Pixel shader stage is connected to output merger stage. Stream output stage is connected to memory resources. Memory resources, buffer, texture, constant buffer are connected to input assembly stage, and vertex shader and hull shader stage, and domain shader stage, geometry shader stage, and memory resources interacts with pixel shader stage and output merge stage, and now this is the end of my presentation. Thank you very much for watching it.